So now I'm recording. Hello to all the people watching later, and let's get started. So last session, we talked about reductions mostly and oxidations, and we kind of did a nice little summary over here where we said that NABH4 was a weak reducing agent, LiAlH4 is a strong reducing agent, DIBA is in the middle, and then we split up our carbonyls into two groups. Group 1 was the more reactive group, and group 2 was the less reactive group. And then we were able to say that in a reduction reaction, an aldehyde will form a primary alcohol, a ketone will form a secondary alcohol, and then both esters and carboxylic acids will always form primary alcohols. And we also covered right here that when you have a reduction, you're always adding at least one hydrogen. But if you have a leaving group, you're going to add an additional hydrogen. So every time we have an ester or a carboxylic acid or something like that, we're going to do the reaction twice and get rid of the leaving group. And we also talked about how sp2 hybridization is favored over sp3, and that's why this reaction mechanism is preferred and why we will end up going to an aldehyde intermediate and then to our final product, which is an alcohol. That was my quick recap. I know it was pretty fast, but we covered it last time. Any questions or anything about the recap before we move on?
Yes, I have a question.
Yes.
So when would you use the sp2 being like better than the sp3? When do you use that?
Great question. So we would use it for this exam. You're only really going to use it in this reduction aspect. So at this point right here, once we did our first round of reduction, we could have protonated or we could have reformed the double bond to kick off the leaving group. And so at that point, we would use this sp2 versus sp3 distinction. And we said that we prefer sp2. So that's why we reformed the double bond instead of just protonating. And that allowed us to go through the reaction 2 times. Make sense?
Yes, thank you.
Cool. You are very welcome. And so the last thing I want to talk about with reductions is this question. So I asked you guys to practice it on your own, just so you could get that condensed formula stuff down. And now I'm going to draw it out for you guys. So first thing is first, we have a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. 8 carbon chain. But I'm going to stop at carbon 7 because we see that it's attached to O2CH3. So what functional group is that? What do you guys think? Yes, it would be an ester. So this carbon right here will be attached to one oxygen, which is the carboxylic acid, the carbonyl, not carboxylic acid, carbonyl oxygen. And then that is attached to another oxygen, which is attached to a CH3. So let's just double check. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And we know that 1, 2, 3 carbons down, we have another carbonyl. So 1, 2, 3. Perfect. And we're going to keep this same general skeleton for the final product. All we did was change our ketone to a what kind of alcohol? Primary, secondary, or tertiary? Secondary. Cool. You guys are so fast. You guys are pros already. So in order to go from this molecule to this molecule, what kind of reagent are we looking for? Someone gave me the answer, which is NABH4. That is correct. But why are we only choosing NABH4? can't we also reduce a ketone with lithium aluminum hydride? And yes, someone in the message thingy got it correct. So the reason we cannot use lithium aluminum hydride is because we are only reducing the ketone, not the ester. And as we talked about before, the ketone is part of group 1, which means it's very reactive, versus the ester is part of group 2, which means it is less reactive and therefore is not NABH4 does not react with it. Therefore, when we use NABH4, this is the product we would get. What if I gave you DIBA as an answer choice? Would that be used to undergo this reaction? Okay, seems like people are saying yes. Would someone care to be my volunteer? And some people are saying no too. So does someone want to volunteer and let me know why or why not they think we could or can't use DIBA? Come on. Someone said it only works with carboxylic acids. The idea is right. It only works with group 2. So we wouldn't be able to use it on the ketone, but it would also work with ester. And then someone else gave me the right answer. So it would stop at the aldehyde. So not only would we not be able to reduce the ketone, we would only reduce this to the aldehyde. So awesome. You guys are doing great. The right answer, therefore, would be A. Any questions on this? This is something that I like to call a name-like question because it's very close to the kind of thing he'll ask you on the exam. And then someone said, was there a specific reagent for DIBA? So DIBA is the reagent. It's just like the shortened name for it. I think it's like di something hydride. I can look it up for you later. But so DIBA is a reagent. You are very welcome. Cool. So we are done with oxidation and reduction. And now we are going to go into the Grignard reaction, which is spelled Grignard. Those weird chemist names. And then one last question about what we just did. Someone asked if we need to know the DIBA mechanism. No, just know that it only works with group 2 and it stops at the aldehyde. He usually doesn't ask about DIBA on this exam, but it does come up on the final. So that's why I talk about it now. Just makes more sense. All right, so before starting the actual Grignard reaction, we're going to talk about our bases, basics, sorry, English is hard. And we're going to talk about what makes something a nucleophile versus what makes it a base. So what did I tell you guys to know about negative charges? Anything with a negative charge is a base or nucleophile. Awesome. So anything with a negative charge is either a nucleophile or a base. Awesome. And so we know that one of the similarities between a nucleophile and a base is that they want to be... Sorry, I stopped in the middle of my sentence. Similarities, they want to be electron rich. And the reason for that is because they are using their electrons to get something or to attack something, right? However, the difference is that a nucleophile wants to attack and bond, versus a base wants to take a hydrogen. So that's the main difference. Both nucleophiles and bases are electron rich. They're going to use their electrons to do something. They like negative charges. However, the difference is that a nucleophile wants to attack and like do a reaction. It wants to attack and bond to something, versus the base just wants to take a hydrogen and that'll make it happy. That's easier than bonding in most cases. So yeah, that's pretty much it. This is a straightforward difference, but sometimes people have trouble with it. So do you guys have any questions so far about what makes something a base versus a nucleophile? Also, sorry if I'm talking really fast or if my voice is shaking. I've had a lot of coffee today. Cool. It doesn't look like there's a lot of questions or any questions. So, moving on. I'm pretty sure you guys have watched or should have watched the lecture where he talks about what a Grignard reagent is and what the reaction is like. So, I'm still going to go over it because, you know, I know you guys. That was kind of shady. I didn't intend it to be. Anyway, I'm used to recording these and like being able to pause and then edit it at the end, and I forget these are live sometimes. So anyway, the Grignard reagent looks like so, where we have a magnesium bromide, right? And the way I like to draw it is like so. If only it would draw. Is it lagging a lot for you guys? No? Okay, cool. So as long as you guys can see it, that's fine. Oh, maybe yes. If only life wasn't so hard. Why is WebEx this way? All right, so for me, it just completely shut off. So let me know if it has started up again. So I had drawn out a CH3 minus and then an Mg plus and a Br minus. But cool, it's not popping up. But okay. So I'm just going to speak and then hopefully it'll turn on at some point. But essentially, I want you guys to think of the Grignard reagent as a carbon with a negative charge, because while it's a carbon attached to a magnesium bromide, the way those bonds work is kind of just like NaOH or something like that. So you want to think of the CH3 minus as separate and then the other part as just a spectator ion, right? And a carbon with a negative charge will actually be a really, really strong base or a really strong nucleophile. So it can work as both. So we're just going to try to keep going. No, I can't draw it, and that sucks. But essentially, the way that we make the Grignard reagent is we're going to start with an alkyl halide. And when we react to the alkyl halide with magnesium, it will make the Grignard reagent. So we have the bromine chill in there attached to a carbon, but then magnesium is kind of a hoe, and it's a home wrecker. So it comes in and it slides in between the carbon and the bromine, and now it's hanging out with the bromine. And that's why the carbon becomes really negative, because it's really sad. It just lost the love of its life. Sounds really bizarre, but now you won't forget that. And my sister in the corner is like, what the frick? Anyway. Okay, and someone wants me to repeat it because, yeah, I know it sounds weird. So we have the bromine attached to a carbon, and it could be any halogen, but I just like to use bromine because that's the most common. So the magnesium is like a home wrecker. So it comes in between the carbon and the bromine, splits them up, it breaks them up. And so now the magnesium is happy, it's all positive, and it's with the bromine, but the carbon is left all by itself, so it's sad, so it's really negative. And I can repeat it again if you guys need. I think it popped back up. So I'm going to try drawing it, and you guys let me know if it works. So as we see here, we have an alkyl halide. And it's chilling, all happy. The carbon and the bromine are attached to one another. They have a nice bond. But then this magnesium comes in and it gets right in here and it breaks them up. And so now we are left with the magnesium bromide drawn. And as I tried to show you guys earlier, but it wasn't really working, instead of looking like the way it's drawn on the handout, it's going to look more like this. They're kind of going to be separate and they're going to have a very loose interaction with one another. And so this carbon is going to be negative. Obviously, it's really sad. It just lost the love of its life. And magnesium is really happy with himself. He's like, oh, haha, I stole his girl, right? And bromine is kind of just like chilling. She doesn't really matter because she's a hoe. But she's kind of sad too. So she's negative. You don't really need to know that much. I just like my analogy a lot. And so, ta-da, you've made the Grignard reagent. And while technically this whole thing is the Grignard reagent, I want you guys to think of what's highlighted here as the Grignard reagent, because it becomes a lot simpler if you just think about it as carbon with a negative charge instead of a carbon attached to a magnesium attached to a bromine. I know that was kind of a lot, but I hope the analogy kind of helped. You don't need to know the mechanism. You just need to know that this is the general thing that happens.
Excuse me, now we're gonna extend the carbon chain with the Grignard reagent.
What?
Sorry about that. I mean that I saw the next exercise. It has like a CH3 with the Grignard reagent. Are we gonna now extend the chain?
Yes. So I'll get into that in just a second. I just want to make sure everyone's good with what we've done so far. But yeah, we're essentially going to add more carbons to the chain. So without further ado, if nobody has any questions or anything, we will go into the reactions. And so for that, you just add an Mg. So yeah, essentially, anytime you see a magnesium, that means we're going to make the Grignard. And so, again, just to reiterate, this is not like the Grignard reaction. The Grignard reaction happens after you've made the reagent. So, just to reiterate, that is the Grignard reagent.
So, if that's not the Grignard reaction, is that the preparation for one?
Exactly. So, this is just making the Grignard.
Okay, thank you.
You're welcome. Okay, so in these examples, I'm going to zoom in to do these, and then I'll zoom back out so you guys can see the whole page. And like I said before, this is drawn as one big glob together, but we don't care about MGBR. We just want CH3 minus.
Excuse me, since it's a ketone, we could attach it to either one, to either carbon.
So you're actually going to attack the carbonyl carbon. So I forgot what I was saying, but that's fine. We're going to attack here like this. Oh, I remember. So first thing we're going to do is we're going to look for an acidic hydrogen, right? Since there's none in sight, we're good to go for the Grignard reaction. So we attack the carbonyl. We move those electrons up. And now we have an O minus. And we also have our CH3. So what can we do at this point? Guys, what can we do? We can protonate. Cool. What's the other option that we talked about during reductions? We can't do it in this example, but what's something that we can sometimes do instead of protonating?
Wait, I have a question. You only added the CH3?
Yes, because we're not going to count the MGBR. The Grignard reagent is essentially, carbon with a negative charge. And since we only have one carbon, it's a CH3. We slap a negative on there, that becomes a nucleophile, and it attacks the carbonyl carbon.
Oh, okay. Thank you.
You are very
So
welcome.
on
Excuse me, it's a
the
problem.
final product that you drew, you're missing a methyl group. And also, like to your question that you were asking, I mean, couldn't we use that, what do they call it? That alkoxide type intermediate before we protonate? Couldn't we use that in like an intramolecular reaction? Is that what you meant?
Yes. So if I understood what you were saying correctly, what I was asking is theoretically, if we had a leaving group, we could have done an intramolecular reaction, as you said. We could have brought the electrons down and reformed a double bond. But the reason we can't do that is because we don't have a leaving group. So the only option we have is to protonate. And once we protonate, we get an alcohol. And as someone also pointed out, yes, I wasn't done drawing the final product. I just got distracted. So if you already drew it, don't forget the CH3 that we added.
But
Thanks.
you mentioned there's something else you could do besides protein.
I'm sorry, what was that?
So, sorry, you were mentioning like a different way instead of protonating, we could do something else.
Yeah, all I was saying is that theoretically, I was just reviewing an old concept just because I wanted you guys to repeat it so you could remember it and kind of understand why we do things. So all I was saying was that in reduction, sometimes instead of protonating, we just reform the double bond. And so I was saying the reason we can't do that is because now we don't have a leaving group since we can't break carbon-carbon bonds. And that's why the only option we have now is to protonate. So any questions? Are we good? I know that was kind of confusing. So if anyone is confused, I'll be happy to repeat anything that I've said. If not, we can just go on to the next one. So someone said, so if there was a leaving group, then we would create a double bond. Well, that is a great segue to the next question, and you can answer that for me. So when we go on to the next question, what does ET stand for? Besides the little alien. Ethyl, exactly. Yes, so ethyl is 2 carbons. So we're going to have 2 carbons with a negative charge. That will be our nucleophile. We're going to attack, kick up these electrons. And so now we have O minus, and we have our 2 carbons that we added. And so now, what will we do?
Oh, we're gonna protonate it now?
So instead of protonating now, since we have this leaving group, we're actually able to kick off the leaving group so that we can reform our double bond and become sp2 again, which is preferred over sp3. So let's just make sure we have our ethyl correctly. But then now, just like in a reduction, LiAlH4 is so strong that it reacts twice, right? The same exact thing is going to happen here. So our Grignard reagent, I'll draw it in a different color now, is so strong that it can go in and react twice. So it's going to come in, attack once more, kick up these electrons again. And so now we have O minus, and we have 2 ethyl groups added. At this point, do we have any choice but to protonate?
No.
No, exactly. So now we have to just go ahead, and I'm just going to move my text really quickly a little bit because I didn't give myself enough room here. And so now we are going to get our final product. I'm so sorry. Which will be an alcohol. Ta-da! That took a lot of effort. But now all we did is we took the carbonyl and made it to an alcohol. We got rid of the leaving group and we added 2 rounds of our Grignard reagent. And someone asked in the chat, does this mean that we need a good leaving group in order to do the second part of the reaction? So everything you learned in Orgo 1 about a good leaving group is not necessarily a lie, but it's mostly going to be thrown out the window for this class, because in Orgo 1, you were essentially told that an OH is a terrible, terrible leaving group and it's never going to leave and like all these things. Well, not exactly in this case. In a carboxylic acid or an ester, it's pretty much always going to leave as a leaving group. So yes, theoretically, if we're talking about real chemistry here, you do need a good leaving group, but we're going to assume that the leaving group is always going to be good enough to leave. And then someone says, how do you know if it will react twice? Well, just like we did for the reductions, you can draw a little cheat sheet summary right here where you can say for every leaving group, you attack 1 more time. So just as a standard, every time we react, we're going to add 1 of the Grignard reagents. And then for every leaving group, we add 1 more of the Grignard reagent. So theoretically speaking, if we had 2 leaving groups, like if we had 2 of these ester structures, we could replace them both and add double the nucleophile. But that doesn't really ever happen. You're usually only going to get 1 leaving group, so you're only going to attack twice. And another question I get a lot is, does it have to say excess? No, in this case, it does not, because you guys have to assume that the Grignard is so strong that it will react to completion. Again, I know that was a mouthful.
Excuse me, you said that carboxylic acids could even if it could be used as a leaving group, but what if we protect it with, I think it was TSML? You can protect it?
Yes, you could, but that's kind of like out of the range for this class. Short answer for your question, yes, you could protect it, and in that case, it may or may not react. But again, it's kind of out of the scope for this class, just because there's so many different outcomes that are possible. I'm sorry if that's not a good answer. But yeah. Are we good to move on to the next one? I don't hear any no's. So what does pH stand for? Also, while you guys are answering that, someone said funny comment. Yes. But someone said like the best comment explaining the Grignard reaction. And so they said that magnesium is like the sugar daddy and bromine is like the sugar baby, and she left the carbon. And so yeah, that's amazing. I love that. I just wanted everyone to hear that. So pH stands for phenyl. And so we know that it is directly attached to the MGBR, right? So that would mean that the negative charge is directly on this ring. If it said benzyl, it would look like this. And I just want to show that distinction because he will sometimes be tricky and give you answers. So remember, phenyl is directly on the ring, benzyl would be one carbon away. And so, same as we did last time, this is going to kick up the electrons. And I'm going to do 2 steps at once. So let me know if it's confusing, but I don't want you guys to have to do a million different steps. So it'll attack, kick the electrons up, and we already know that the electrons are going to come down and break the ring open. So we can actually draw that all in. And I'll go ahead and draw a line here to show what bond we're breaking. And so now, as I always say, we count carbons 1, 2, 3, 4, 5. So I'm going to go ahead and draw a 5 carbon chain. And I always like to start with the carbonyl, but it doesn't really matter. Bam. So on carbon 1, which is the carbonyl carbon, we are going to add our Grignard reagent. Bam. And then on carbon 5, we know that we have our O minus, because the leaving group, since it's a ring, doesn't actually leave. The ring just gets broken open. And so now at this point, yes, we need to protonate, but I like to save the protonations for the end just so we can protonate them all at once. Doesn't matter how you do it.
Sorry about that. Can we get rid of the other leaving group?
What do you mean?
Like, sorry, I mean like use the Grignard reagent again.
Yes, that's what we're going to do. So, what I was saying, that's okay. So we know that we have another molecule of our Grignard reagent. So we're going to attack one more time, kick those electrons up. And now we still have that negatively charged oxygen because I chose to protonate it at the end. And now we no longer have that double bond. We just have a negative charge. And we have 2 phenyl groups, which I'm trying to draw sideways, and it looks horrendous, but that's fine. You guys get the idea. Bam. And then the next step, I guess I'll draw it out again. So in the next step, we're going to use H3O plus to protonate both of those O minuses. And I'm just going to write pH because I don't want to draw them again. So again, pH means phenyl. So again, since we had a leaving group, we added 2 moles essentially of our Grignard reagent, or 2 molecules of it, and we attached 2 phenyl groups to that carbonyl carbon, and we ended up turning the carbonyl into an alcohol. And one thing I want to point out, because it's a question I get every single semester, is how do you know when there's too much steric hindrance to do it again? Because at this point, it kind of feels like this ring is a really big and sterically hindered group, so why would we go in again? That's a question I asked as well. As far as the Grignard goes, it's pretty much just going to do the reaction to completion, no matter how hindered it gets. So we're just going to pretend steric hindrance doesn't matter for this reaction. And then someone asked, does it have to be H3O plus, not H2O? No, I just assumed that I gave you guys H3O plus. You can definitely do the same thing with H2O. So let me fix that. And then someone asked, why didn't the oxygen at the end leave? So when we have a ring that we're breaking open, even though it's a leaving group, it's not going to actually leave. It's just going to open up. So there's nothing to like attack here and kick off the leaving group, because whatever we want to attack is actually going to go to the more electrophilic carbon, which is this one right here. So we're essentially going to leave this alone and just protonate at the end. Makes sense? Cool. I'm going to take that as a yes. And we're going to move on. These two are pretty much the same. So I'm going to go ahead and do one of these examples. I can go back and do the other two if you guys want. But again, it's more of the same. So I think you guys can practice those on your own. This is the one I want to go over. I'm very excited to go over it because it's big and ugly, right? And it looks really scary. So I will help you with the first step, which is drawing out the actual Grignard reagent. So again, we get rid of MgBr and we know we have CH3 with a negative. And I'm going to give you guys a minute to look at this and kind of think about what you think is going to happen. I won't put you in groups or anything, but I just want you guys to have like a minute to just think about it. And then I'm going to ask somebody to help me with the answer. And then just so it's not an awkward silence. Oh, and also while you're doing that, to anyone who didn't sign in on the attendance, please do so. I will heart you forever. Okay, I think it's been a minute-ish. So let's do the thing. I wasn't keeping track, so hopefully it's been like a minute. So does anyone want to tell me what they think is going to happen?
Well,
There's an acidic proton.
Wow, yes, exactly. So this was another trick question, but you guys got it because, duh, you're amazing and you're stellar, and I knew you would. So can you please point out which one of the hydrogens is acidic, please? And I know it sounds obvious, but do it anyway.
One on the hydroxyl group.
Yes, exactly. So it is on a heteroatom, so it's going to be acidic. So this is actually going to be no reaction because there's no Grignard reaction going on. But since you guys are super smart and amazing, can you tell me what will happen instead of the Grignard reaction?
Acid base.
Acid base, exactly. Cool. Okay, so we have another very similar question here, and I left it in condensed formula for you. So this is, again, kind of like how Dr. West will do it. So take a second and try to draw these out on your own while I explain a question that someone asked about the previous one, and then we'll go over it together. So some person asked why no Grignard, and then someone also asked a similar question, which was, so the acidic proton kind of takes precedent over Grignard. So yes, exactly. When you have a acidic proton present, that means that instead of being a nucleophile, it's going to be a super strong base, because if you think about it, it's a lot easier to just steal a hydrogen than it is to attack, especially when there's so much stuff going on right here. So instead of being a nucleophile, it just steals this hydrogen and you get an acid-base reaction going on, not the Grignard reaction. that wasn't a good enough explanation, I can try to be a little bit more in depth. But let me know what you guys think.
Excuse me, can the answer be D due to the hydroxy group or no?
Sorry, what?
Could
Yeah.
D will not form a Grignard reagent?
Oh, yeah, we're getting to that, so just give me 1 second, because people were still asking about the one before. But I like that you went ahead and did it. One more question. So someone asked, it's because of the acidic hydrogen. Exactly. And since I wasn't able to write it earlier, I'll visually put it here for you guys. So Grignard will not happen with acidic hydrogen. And someone tell me, what is an acidic hydrogen? What's an example? I said it earlier.
Heteroatom.
Heteroatom, exactly. And then someone
Bond.
said triple bond.
Terminal icon.
Triple bond. Or carboxylic acid. And by that, I mean this hydrogen right here. Awesome. So for this next one, you kind of don't really need to draw them all out if you have enough practice at looking at these and figuring out what functional group each thing is. So right here, what functional group will that oxygen be a part of? Ether, exactly. So this is an ether. What about this one right here?
Isn't that an ether?
Yes. Here we don't have anything extraordinary going on for C, so that's a really basic one. But here,
So we call it sorry.
what was that?
Did I call it alkyl halide since it's the bromide?
Yeah, so it's an alkyl halide. The only reason I didn't write that was because technically they're all alkyl halides. So I didn't want to confuse anyone, but yes, so all of these would be alkyl halides. And then in this case, we have an OH group, so that would count as an acidic hydrogen. And so D is the correct answer. This would be no reaction. And someone said aldehyde. I think I might have. I'm very sorry, guys. So this is actually supposed to be CH2OH. But you are absolutely right. The way it was written, it would have been an aldehyde. I'm sorry for the mistake. So please correct it if you have the handout and you're filling it out, because I don't want you to get confused. It would be a CH2OH, so then it wouldn't be an aldehyde. It would actually be an alcohol.
So, Rosemary, I have a question.
Yes.
Why would protons attached to a double bond not be considered acidic?
So they are acidic, and that's a good point. I remember I looked this up, and it had to do with how acidic exactly different things are and what the energy required is to steal a double bonded hydrogen versus attacking the carbonyl. And I believe it had something to do with the activation energy for both of those reactions. And I believe that as far as Dr. West goes, double bonds don't count. And I know that's not a great explanation, and I apologize, but I can look into it just to refresh my memory and let you guys know. But I don't remember exactly off the top of my head.
Okay, so it probably just has something to do with kinetics and not necessarily with theory.
Yeah, exactly.
Excuse me?
Yeah.
How would I know, like, if there's two oxygens, how would I know if one's, like, a double bonded with carbon and, like, an ester versus, like, ethers, like,
Great question.
you know what I'm talking about?
Yeah, so let's say you have something like CH2O, CH2. We know that that would be written out like that. And then obviously this would have an R group, that would have an R group, right? Versus if it was written CH.
Excuse me. Wait, can someone mute their mic real quick? Because I just hear like airplane. Like,
Yeah. There you go. Thank you very much. So if it was written CO2 CH2R, kind of like that, that would mean that you have an R group attached to this carbon, which is double bonded to an oxygen, and then bonded to the other oxygen, and then we have a CH2 and an R group. I stuttered a little bit on that last part. But yeah, okay. You're welcome. Cool. So you guys actually got through so much today. We're going to go through the rest of these reactions on Friday. So we ended in the perfect spot. And these next questions we're going to spend some time on are kind of like putting all the concepts together. And it might look scary, especially this 5-part question, but it's not too bad once we talk about it. And then I'll obviously, after I give you the real scientific long explanation, I'll give you the rosemary method, which is totally trademarked. That's my thing. And it'll be super quick, and hopefully you'll be able to do it easy peasy. Any questions, comments, or concerns before I let you guys go?
Excuse me, when are you gonna be uploading the handout to like to stuff on our own?
So I can't upload the handout anymore because Dr. West had to like change the Canvas settings, so I can no longer upload things. So I will be sending them in the emails on Mondays that I send out. So the chapter 12 handout was sent this Monday, and I believe last Monday, but I could be wrong. And then someone said, will we start chapter 13 on Friday? Depends on how quickly we get through these. Usually doing these examples takes approximately one whole session, maybe like 30 minutes. So I was thinking of spending whatever time we have left just quickly reviewing and doing some more practice problems about chapter 12. And then we just start chapter 13 fresh on Monday. I know Katrina's been doing Kahoot games, and that sounds like a lot of fun. So I might end up making a Kahoot game to play on Friday, but I'm not sure yet. Okay, cool. So bye, guys. See you later.